If you feel you've reached your limit with mathematical limits, this is the video to watch. But if your learning material has not tended to that subject yet, you can get a nice head start today. Some of the concepts in mathematics may seem like it's problem children. They don't fit nicely into the basic calculations, standard methods, or more general characteristics. Concepts like infinity, undefined, division by zero, discontinuity. In many of these seemingly problematic concepts, limits play a very important role in handling the strange cases and outliers. And when they are managed correctly, you realize they actually form an unmissable subsection of mathematics, one without which mathematics would have been a lot poorer when it comes to applicability, depth, and variety. Let's consider a relatively simple example of a limit and what each element of the formula represents, followed by a practical scenario that can be represented by this limit. We use the shortened lim to indicate a limit. The limit is accompanied by some kind of variable which is associated with the point at which the problematic concept rears its head. Often this point corresponds to extremes, for instance when the variable tends to infinity. Something feels strange when one tries to think about infinity as a specific number, since whatever that specific number is, you could always add 1 to it to get a larger number, which means that specific number was not infinity. You could almost describe infinity as the smallest number to which we cannot count. But it's better to not think about infinity as a number at all. We use the arrow to indicate tends to, which means the variable gets closer and closer to the target, but don't actually ever precisely hits it. We are then interested in what happens to some outcome or answer as this variable approaches the target or point at which the problem occurs. The outcome is usually represented by a function, in this case a half to the power a fifth of the variable. For each 5 units with which the variable x increases, the power of a half increases by 5 over 5 equals 1. But let's visualize it. Sam is back and is once more heading to his car to fetch his backpack. But this time around, the following restriction is placed on his movement. Every 5 seconds he has to halve the distance between him and his car. At any point in our example, he can therefore only ever walk half the distance between himself and the car at that time. Let's say that the current distance, which we'll display on the y-axis of the graph, is 1 unit. We say that the point in time, which we'll display on the x-axis in seconds, is the point 0, the start. Sam can therefore walk half this distance during the next 5 seconds. We can see how the function in our limit starts forming on the graph as it moves from 1 on the y-axis to a half as the 5 seconds played out on the x-axis. Now Sam can walk half of the remaining distance and he can continue like this. Each time the distance between him and the car gets smaller and smaller, but each time he's only allowed to take a smaller and smaller step towards the car. Theoretically, he can continue like this forever, but never actually really get there. The distance simply remains slightly larger than 0. If it wasn't for limits, this picnic would be doomed. It goes to show what mathematics can do for you. Limits allow us to solve that problematic point. Rather than trying to say the value of the function in the point infinity is 0, which does not make technical sense, we can say that the value of the function y tends to 0 as the input value x tends to infinity. It doesn't sound like much of a difference, but technically it is. And other limits could of course be a lot more elaborate than our example. We now have a graph for x greater than or equal to 0, and we see that it tends to 0. But let's quickly consider the other side of the graph. What would the step before our starting point be if the same situation and rules were in play? Well, Sam would have had to be twice as far from the car. We have to adjust the scale of the y-axis to display larger distances. So, 5 seconds before, Sam would have started 2 units away from the car. And in those 5 seconds, you could walk 1 unit closer, or rather jog, or it'll take him way too long. And what about the previous 5 seconds? Then he would have had to start 4 units away from his car and run 2 units closer in 5 seconds. We see that the distance y doubles for every 5 seconds that x moves to the left, and halves for every 5 seconds that x moves to the right. Of course, this corresponds to the original function over which the limit is taken, namely half to the power of a fifth of x. This distance is clearly increasing drastically as x moves to the left, and as we allow x to keep moving to the left, we can say that the limit of the function as x tends to minus infinity equals infinity. And that's the basic idea of limits. In our next video, we'll consider a few more eventful limits where discontinuity occurs. Remember to tend back to the channel or turn on notifications to be reminded of the videos.